I think we'll get started. It's a great pleasure to welcome Valentin Negal for today's talk, the CBS seminar. Valentin is a physicist. He did his undergraduate in Göttingen and then transitioned, like many physicists, for his PhD into neuroscience, which he did at UCLA in Los Angeles, where he started to look at the sort of biophysics of synaptic transmission in hippocampal slices. And one of the few things he told me he regrets in Los Angeles is that he didn't start surfing there. He just focused on neuroscience rather than enjoy the beach. He then, for his postdoc, moved back to Germany and started his project in the lab of Tobias Bonhoeffer. And this is where we almost overlapped. This was in 1999 when I left and Valentin arrived, and he sort of followed up with imaging. And I think to summarize, his task in Tobias Bonhoeffer's lab was to clean up after the mess I left. That's what he what he told me. It's also where he was one of the first to use super resolution microscopy. And it's not PALM or STORM. It's one of the things you probably all have heard about. It was STED, which is stimulated emission depletion microscopy. It's what Stefan Hell got the Nobel Prize for. The problem with STED is that it's much, much harder to implement than PALM or STORM. So I think why PALM and STORM have taken off is because of the simplicity with which it can be applied. STED requires intricate, delicate fine-tuning of the system. And that's why I think there's relatively few working systems still in the world. And I think Valentin is one of the very few who realized that STED is something that has a specific niche, namely to do imaging in thick tissue, in live tissue. And that's what he'll gonna talk about today. So he developed this technique in Tobias Bonhoeffer's lab and then got a faculty position in Bordeaux in France. So now he goes not by Valentin Negal, but by Valentin Negerl. So it's harder to pronounce. But, and the institute where he's working now has a focus on super resolution techniques, and Valentin is the one who really took this and developed it into an extremely powerful technique to look at live tissue. The further development was looking not at the, he didn't fill cells to visualize them, but he's looking at the extracellular space, and he came up with a really cool acronym for that. It's called SUSHI. There's also some affinity to Japan, generally speaking. So SUSHI is a super resolution shadow imaging, and he'll talk a lot about that. There is apparently, I've heard about that, an expansion of that, which is called sashimi. I don't know what it stands for, but maybe Valentin will briefly address that. I think the projects he used this for within neuroscience are extremely impressive, and he'll tell us more about this now. So thank you, Valentin, for coming.
All right. Thanks. Yeah. Thank you for this very nice impromptu introduction. Yeah. So yeah, it's great to be here. I was here some 17 years ago, just on a visit. Florian had just been hired to Harvard. He was a young, promising scientist, and at the time the rage was two-photon microscopy, and actually that's what I've followed up on. Not cleaning up his mess, but benefiting from the crumbs that he left me in Munich, and I could develop this and go from two-photon to these higher resolution approaches in the years to come. Okay, yeah. So I want to tell you about our exploits, or actually some of the methodological developments we've recently undertaken, particularly using SLED microscopy. So for just a little outline, I will talk about exactly this technique that we published last year called super resolution shadow imaging, SUSHI, and then also present something that we just recently also managed to sort of complete, and this is a combination of various super resolution techniques, sort of joining combining and looking for sort of a best of both worlds approaches. 'Cause in the past, sort of the super resolution approaches like like Palm and Storm, these stochastic type approaches, have been sort of developed independently or sort of almost in competition, it seemed, to these deterministic approaches like STED. And then we thought, why just let's stop this war and just combine and join hands, and maybe we can build a microscope that can benefit from both. And I'll present you just briefly on the results of that. All right. So this is our general fascination. Is this incredible transformation of things and how the brain accomplishes that. Unfortunately, what I think about the brain was so amazing is this integrative capacity. So in space and time, we can link things over decades. Some photons coming from the dawn of the universe, and they get us excited, and it's all sort of a huge integration machine, huge computer with incredible memory and ability to interact with all kinds of things, right? So that's amazing. Unfortunately, we don't work on this really, but we work a little bit on the structural underpinnings, structural complexity that allows the brain to do all these wonderful things. And so how we do it is, sort of classically we're using the mouse brain as a model system in slices, also in vivo, combine these new high-resolution approaches with traditional electrophysiological approaches, add to that a bit of mathematical modeling to get sort of like another perspective to bridge the gap between theory and experiment, and then also combine that with behavioral analysis. Yeah? Now, we do that not in the mouse, in the human brain. The mouse brain much smaller, 1,000 times smaller, but equally amazing transformations that occur there, right? So, all right. So this is we'll start off with our sushi technique. So this is sort of the summary, and if you understand this this picture, then you have learned something about actually how it works, right? All right, so the key word here is visualizing the extracellular space, as Florian already alluded to. And so what is the extracellular space? So it's, by definition, the gaps, the space that surrounds all brain cells. Right? I mean, it's not just, any extracellular space, obviously it's not just something specific about the brain. Any organ where there are cells, well, there's going to be extracellular space, right? It is anywhere. It is filled with really this interstitial fluid that is actually quite juicy in the sense that it's not just a clear fluid, but it's full of proteins. It's actually quite dense. It's quite viscous, actually, right? And it's sort of wrong to think about it just as an empty space. It's really as jam-packed as really the intracellular space. It just happens to be called the extracellular space. You could even invert it. You could call the extracellular space the intracellular and vice versa somehow, right? But there's a lot of things, but certainly we know much less about it. It occupies a whopping quarter of the brain, and that's excluding the ventricles. So it's just just the space actually between the cells occupies that amount of fraction, right? It is, as you can imagine, spatially very complex, because it's basically the negative space of all cellular structures, and the cellular structures are very complex and convoluted, so it's just sort of inverting that, and that has got to be very complex as well, right? Being then only a quarter of the whole volume, it means it's sort of as complex, but smaller, sort of compressed compared to the intracellular space, right? As any extracellular signal, by definition, or any, basically all molecules that mediate intercellular signaling, except those that go through gap junctions, they have to transit through the extracellular space necessarily, inevitably, right? And by virtue of that, they have to be influenced by sort of the biophysics, the structure, the geometry, the viscosity, and so on, the diffusivity of the space, right? represents a reservoir for obviously ions, important for neuronal excitability, potassium, sodium, and so on. And then is obviously, as I said, the passageway for signaling molecules, and also sort of energy supply, nutrients, so ATP and so on, or sugar and so on goes via the extracellular space. And then for sort of clinical importance, it's sort of the last meter, last micron for the actual delivery, the reaching of the targets of drugs in the brain. Right? There's one thing is to cross the blood-brain barrier, but then there's sort of the parenchymal barrier, the extracellular space barrier that you need to overcome to actually reach the cells and reach your pharmaceutical targets. So that's all very interesting. And then the other interesting thing is, as I already said, the extracellular space being the inverse space of all cellular structures. I think it's interesting to study ECS because it will give us a chance to actually observe the cellular structures, negatively speaking. Right? Okay, so the problem is in the past there's been a lack of sort of dedicated investigation tools in live tissue, in thick tissue, to really visualize it. And I think part of it has to do with certainly a technical challenge. It's not obvious how to really do a good job at imaging it. But then there's been a sort of a cultural bias, I would say, to things about that happen to signaling pathways, signaling events happening on the surface of the cell, and especially inside. People really get excited about that. On the outside, it seems sort of trivial or irrelevant, but that's not true. Okay, so traditionally, what are those tools? So they have been for many decades biophysical tools, very precise, very reliable tools to quantify the extracellular space, such as integrated optical imaging or real-time iontophoresis. But these are bulk measurements. They don't tell us anything about the structure, the microanatomical structure of the extracellular space. Basically, these are techniques where you inject some substance in a very local fashion and just see how it spreads in the complicated maze of the ECS. And then you just measure somewhere else, some 100 micron or a millimeter away, the time it takes for the stuff to emerge there, either iontophoretically or with fluorescence, and then based on some model, make some assumptions about, well, how must the thing look like, yeah? You can imagine it's not a definitive way of studying it because it's very sort of degenerate. There's many kinds of different solutions, many kinds of different structures will give you the same result, right? Then there are MRI-based techniques, which don't have a whole lot of resolution, as you know. One voxel of an MRI image corresponds to or can contain up to 1 million cells. So we are far away from cellular resolution. Also, a priori, in this diffusion tensor type MRI imaging, you measure basically the flux of water, anisotropy of water movements, water molecule movements, and that a priori cannot distinguish between water inside or outside the cells, right? So it's not really a technique that targets the extracellular space either. Yeah? And then, of course, we have the gold standard for ultrastructural analysis is electron microscopy, which gives you all the resolution that you want, but it requires tissue fixation, and that we know is prone also to serious, or can be prone to serious fixation artifacts. One indication is that in traditional EM micrographs, if you look for the ECS, you have a hard time finding it because it's basically depleted, basically gone. Yeah? So something happens in the fixation process, or some stage of the processing that essentially depletes the ECS. Yeah? So that's not good if you're, even before you've started looking for it, it's already gone. Right? Okay, and then we have fluorescence microscopy techniques, recent strategies based on super resolution microscopy, which can actually access that space. Yeah? And I'll tell you about this now. All right, so just as a reminder, fluorescence microscopy, great technique, live cell imaging, non-invasive, kind of has a depth penetration but you have to label your targets, obviously. There's no intrinsic contrast like in EM, right? So we have to fill a single cell, make it express a protein. And of course, we can do that for a lot of the cells, or in this case here, the trees. But this would be a very laborsome to paint all the trees, right? And if we were to do that, and that's the brainbow strategy a little bit, right? If we do that, and so we can do that, yeah? But if you do it really to all the cells, there's a little bit of a problem that you're seeing too much, right? Yeah, it's like a glare. There's in fluorescence microscopy, you usually want to have, if you're really interested in the high resolution stuff, sort of the subsynaptic, subcellular resolution, you want a labeled structure that stands out brightly in a black surround, right? And you don't want too many structures to be co-fluorescent at the same time. Right? So, but in reality, you want to see the majestic screensaver scene, but this is hard to realize. So we took the inverse strategy, and that is instead of labeling all the trees, filling all the cells with the PET pipette, rather do this, which is basically to, instead of doing that, so we put a dye now into the air, into the fog that surrounds the trees. So instead of labeling all the trunks and the leaves and so on, we just color the air that surrounds the trees and just sort of pump the fog into the forest, and then take an image, an inverse image, like the outline, right? And that proposition is not entirely stupid, because the extracellular space is just a fraction. It's not at 1%, but it's 20%. So it's not like 80%, where then again you would have this problem of glare and having too much label. But the label is, even though it doesn't sound intuitive, it's not intuitive maybe, is relatively sparse, because it's just these little crevices between the cells. But still, it's not super sparse. It's kind of everywhere, and you did a really good microscope to constrain your fluorescence and have a really nice small point spread function and so on. So here comes super resolution microscopy to the rescue, and that really makes the difference. So a priori that our labels, our reporters, like GFP or organic dyes, are as small as we need them to be, just a few nanometers. GFP is 2 or 3 nanometers, yeah, can relatively to the structure we're trying to resolve, that's fine. The problem is when you try to read out the fluorescence, as you know, because of the loss of diffraction of light, you end up with a big fluorescent spot. Yeah? And that has to do with the fact that light behaves like a wave, and you cannot focus it. You cannot focus electromagnetic energy, for that matter, into a spot that's smaller than roughly half the wavelength of the light. Yeah? That's just a law of physics. However, Stefan Hell, as Florian mentioned, right, invented this great strategy technique of stat microscopy, which actually manages to shrink down the extent of that fluorescent blob by, and this is now just in a couple sentences I'll explain it, by using a second laser beam, looking sort of at the sort of antagonistic action of 2 laser beams, with the excitation laser as in a regular 2-photon or confocal microscope. But that action is antagonized by the action of a second laser beam that's neatly superimposed on top of the original one. And that second laser beam does the exact opposite, both in space and in terms of what it does photophysically to the fluorescence. It de-excites the first, doesn't excite it, de-excites it. And it does so everywhere except for in the center. So in the center you have a maximal fluorescence because of the excitation laser, induced either by a 1-photon process or 2-photon process, doesn't matter. And then all around it, you have the second laser, which does exactly the opposite. But it tries to you try to spare the center. How can you spare the center? Well, you use interference. That's because of the wave-like nature. Also, you exploit that and create effectively a 0 intensity minimum, or very shallow profile of the intensity of this stat laser that does the inhibition. So you combine the two, and then you end up with a point spread function that is much smaller. It doesn't quite yet reach the 3 nanometers, although I think the sort of under perfect technical conditions in the lab, some special dyes, actually the Hell Lab has actually achieved that, kind of reached that single digit nanometer resolution. Yeah? But for practical purposes now, we can achieve around 30, 40 nanometers in XY, and also now extend this actually along the Z-axis, along the optical axis of the microscope, which is a bit more tricky. Yeah? So then you end up with a volume resolution where you go from a femtoliter, which is around the size of a synapse, bit bigger. Right? The volume of a big spine, a big juicy spine, is around a femtoliter, a cubic micron. And then increasing the resolution by a factor of 10 in X, a factor of 10 in Y, and in Z, you have a gain in volume resolution up to around 1,000. And that's a whopping number, right? That's where physicists say, all right, okay, that's maybe interesting. Yeah? Maybe worth to pursue. So I'll maybe skip that in the interest of time. This is just now how we realize this resolution in 3D. So we're using adaptive optics-based strategies, but too slowly, so I'll skip that just to show you here the curve of the comparison of the point spread function volume that we can achieve with regular two-photon microscopy. It's a few hundred attoliters, so half a femtoliter, and then confocal, you drop down, and then with a 3D STED approach, inhibiting the fluorescence X, Y, and Z, you go well below 1 attoliter. An attoliter is really, really small. We do this on, or we achieve this on microscopes we built in the lab using all, typically commercial components. We don't have a wonderful machine shop or anything. Now we just order things from Thor Labs and Nels Griot and so on, so we know the catalogs very well. This is sort of the back view. This is sort of the people who do the sort of optic engineering, spend most of the time on this side of the table, and then the biologists, I don't have the view, spend on the other side. And sometimes the biologists and the engineers actually are the same person in one, right? That's of course ideal. Okay, now about the labeling strategy for the sushi. We can either do the most simple thing in the book, and that is this is now talking about brain slices, organotypic brain slices or acute brain slices. We can either just bathe the whole specimen in an ACSF that contains the dye, and this is an organic dye like Atto or Alexa originally, when we started with that. Or you can just spritz it in with a pico spritzer and a patch pipette in an area of your choosing. Yeah, there's advantages and disadvantages to both. And this is the spectral scheme here, depending on we do 1 photon excitation or 2 photon excitation. And then the STED, we take normally, or not always de-excite here at this wavelength around 600 nanometers. Yeah. And then we realized that we can also get away with calcine, which is much cheaper than the Atto Alexa dyes. This is maybe a consideration, given that the volume of the dye is actually rather large. If you bathe the whole chamber with the dye, right? Okay, so then we get images like this. When we do the bath application of the dye, we get these shadows, hence the acronym, shadow imaging. Goes back to this technique called shadow patching that maybe some of you are familiar with. And you see these nice shadows here in this, the cell bodies layered organization, the hippocampus. It helps to flip the lookup table around, just for recognizing contrast and structure in the images. Turns out the labeling is it's very straightforward. It's sort of fail-proof. Yeah? You can wash it in rapidly within tens of minutes or minutes even, and get contrast, and then wash it out also. There's no bleaching when the dye is put on the outside. You can see on the extracellular here, this curve, there's no bleaching over time because there's an infinity of dye molecules in the extracellular space that will continuously replenish themselves. And then we've checked at just potential deleterious effects on the cells. and we didn't see any obvious ones. Yeah? Wouldn't be expected because these are vital dyes. They're used for intracellular recordings frequently, and there's really no issue. So when we record basic membrane properties, passive membrane properties, or also synaptic functions, we don't see any issues when we put the dye on the outside of the cells. Okay, just to show you some comparison here. So you can do the technique also with a 2-photon. You get some shadows, but clearly the 3D stat is greatly improves on it, and you can really see the neuropil much more sharply. Just some more images here. So again, after inversion of the lookup table, you get all this nice contrast, and the contrast is afforded relatively cheaply obtained without actually having any fluorescence here. And all the white stuff is actually black, right? There's physically no photons that are being used to generate this image. Hence, if there's no photons, there can be no bleaching. There can also be no toxicity in all of these areas. So basically, we can get a large spatial contrast without paying 80% of the bill. We're only paying for 20% of the bill, basically. Yeah? So it's a good discount. And then just from the morphology, because cells have such a distinctive, especially neurons have such a distinctive anatomy, we can tell what kind of cells we're looking at. Is it pyramidal neurons, interneurons, glial cells, and so on. Yeah? We don't need to do a complicated functional analysis or post-hoc immunofluorescence or something. Yeah? We can tell right away. We can take large areas, which takes half an hour or so, or even longer, because we have a single point scanning system with 20 nanometer voxel pixel size, and then it takes obviously a long time to scan up this area. We can zoom in then, and you can see here, which was really striking at the time for us, that we see a lot of black spaces. So after signal inversion, there's a lot of black space corresponding to these numbers from biophysical studies that had all along for decades indicated, in contrast to the EM analyses, that the extracellular space actually occupies a large fraction of brain volume. So this is actually sort of the view, the classic EM view. This is from a paper of the Graham Knott lab in Switzerland, where they compared a chemical fixed tissue under the EM with cryo-fixed tissue under the EM. And you can see that classical chemical fixation protocols make the ECS really be sort of monotonously thin and really depleting it. Whereas after cryofixation, you have these much more voluminous heterogeneous spaces. Now, which is the reality, we don't really know, and this a priori, right? And this is, I think, where our approach can weigh in and sort out what's more realistic, yeah? What's more real. So with this technique in hand, we can now be quite quantitative about the volume fraction, for instance, of the ECS, which is kind of like a bulk property, right? But we can do this now spatially resolved. We can measure the volume fraction in a local area. And taking to the extreme, we could measure the volume fraction even around a single synapse, right? And say, okay, this synapse, this type of synapse has this amount of ECS distribution around it versus another area. Yeah? So you can, for instance, in this example, you can see here that in this area here, this is the CA1 area in the hippocampus, depending on whether you're in the cell body layer or stratum radiatum or oriens, you may have quite distinct volume fractions. Yeah? And this could be important, just from sitting in a rocking chair and thinking about it. It could be important for the way how biomolecules, can spread around in that area, right? This is here the ECS is much less, but it's much more orderly, if you will, because it's just stuff can swish around just around the cell bodies. And here it's much more complex, much more convoluted, the space, but overall it's more voluminous, the extracellular space. Yeah. So how is diffusion now affected? Thinking about not diffusion of molecules on the synaptic cleft, because that's probably not going to be affected. But diffusion outside of the synaptic cleft, there's all kinds of things that are diffusing around outside. Think of volume transmission, think of nutrients moving around, and so on. And so how they move around, actually, we don't know. If you try to look at the literature, it's amazing how little we know about transport processes, diffusive or convective, in the brain. We don't really know, and there's some controversies, but they're not really driven by a whole lot of data. And then we can measure the widths here of the extracellular space, looking at line profiles, and we arrive at numbers that are consistent with the EM based on cryogenic fixation, and also with recent super resolution imaging by colleagues of ours in Bordeaux using carbon nanotubes. So this is a technique based on single molecule imaging, little exogenous reporter molecules that sort of snake around the extracellular space, and from that they could derive the physical structure of the extracellular space. And these numbers that they arrive at really agree well with our direct imaging approach. Yeah? We can now look at physiological responses of the extracellular space to now some stimuli. Right? In this case, an osmotic challenge, which is not necessarily so physiological, but under some extreme edema or ischemia conditions, you can imagine this to occur. And indeed, we can see that increasing the osmolarity in the extracellular space increases the extracellular space transiently. Yeah? We see an increase here in the black spaces, right? So the width increases, and this is totally expected because if you add the osmolarity outside transiently, you get a shift of water from the inside of the cells to the outside, and that should expand the space. So things are behaving as it's kind of expected. Then we can also look at more physiological things. Look at neuronal activity on a big scale. For instance, inducing epileptic discharges pharmacologically in the brain slices, and then pair those experiments with actual electrophysiological recordings to see how, whenever the slice undergoes sort of an ictal event, how does the ECS, the extracellular space, react to that? Yeah? And when we do that, indeed, we can see that during spiking activity, a sort of massive synchronized activity, where there's a lot of ion fluxes going on, right? We get effectively a squeezing of the extracellular space. Yeah? The cells just swell up, and I'm sure you've seen that in your own slice experiments, that when there's a lot of activity, your slice seems to move, move around, and this is, we can now actually see that reflected in the extracellular space. All the cells just transiently expand, and the extracellular space basically gets transiently depleted. Yeah? There's also, you can see that in these transmitted light, and this basically intrinsic signals are sort of the source of that. Yeah? On the other end of the sort of X spectrum of the activity level, now not simulating the whole slice, but just activating a single synapse, we can also see that this entails quite significant changes in the extracellular space. Yeah? And this is we could see that after 2-photon glutamine encaging on a single spine. We could see that upon repetitive stimulation there, we see a whole sort of very complex spatial dynamics right around the synapse. We know that with such a paradigm, you can induce spine plasticity. People have done that, have consistently seen that when you stimulate single spines repetitively, that you will induce some growth process. Spines become larger, they incorporate new synaptic receptors, but they haven't really looked at yet at the space around it. So what happens then around it? Yeah? And now we want to know whether what happens around it is this just sort of following passively the cellular structures, or are the dynamics in the extracellular space actually maybe reflecting some active process? Is this sort of instructive? And I don't have answers yet, but we are definitely going in that direction now. And then, and if I'm going way too slow, just quickly show you some other applications here. We can combine the inverse labeling strategy with regular positive labeling of cells. So you can see a YFP labeled cell. You see a lot of actually shadows inside of the cell. So this is a YFP expressing cell, so YFP all over in the cytosol, except for the organelles. Yeah, so this is intracellular sushi. Yeah. And then we now can see that cell nicely vis-a-vis the surrounding context. Yeah, and this is, I mean, you can imagine this could be very interesting, some studies. With the benefit of this contrast, this inverse contrast, where sort of the minority of structures are labeled, we can have a chance to see things that ordinarily you would never see in a light microscope. For instance, synaptic clefts. Yeah? Together with the inverse contrast labeling, plus the high spatial resolution of the 3D SLED approach, I think with a little bit of imagination, you can see here a synaptic cleft between this bouton here, putative and the spine, and as well as between this spine and this bouton. Okay? We don't have the resolution really to measure the synaptic cleft, because it's sub-hour resolution. The width here of the cleft is hardly 47 nanometers. It's likely to be much smaller. But I think we could do some sort of relative measurements, looking at then integrated fluorescence levels and look at before and after scenarios. Right? Another example is here, a synapse formed between the mossy fibers, the giant mossy fiber terminals from CA3 pyramidal neurons onto the dendritic excrescences of the granule cells, mossy fibers, onto the CA3 cells that form these dendritic excrescences, these very complex multi-spine synapses, and also with a little bit of imagination, you can see sort of the outline of the synaptic cleft. Yeah? And this is certainly would be invisible with regular microscopy, but also with regular SLED microscopy. You really need this inverse contrast. Let's skip through that. So we can also look at astrocytes. So we can co-label it, and this is sort of nice now to reveal the astrocytic morphology, which is also very complex. You really need a good microscope to see it. But at the same time, see all the surrounding cells that they're sort of, and the astrocytes really penetrate the neuropil. And there's hardly a micron that doesn't have astrocytic process in it. So we don't have sashimi, yeah? But we have, what do we have? We have koshi. So if you don't have the money to buy yourself a SLED microscope. Tushi works great. Doesn't have quite the resolution, as I said. And then you can definitely do it in zebrafish. Yeah? But if you want to be more general, call it fushi, please. Yeah. Yeah. Okay, then actually I should skip. Actually, I'm going to skip through this. We have some did some baby steps now in doing reconstructions. And I think there's some promise in using sushi as a reconstruction technique in live tissue. We still need better resolution, and I think it needs to be paired with positive labeling to really confirm that this is really that we're identifying structures correctly. But I think there is some potential in this. I want to close out on this with I think the most interesting application, and this is really time-lapse dynamic imaging, using sushi as a way to sample the given field of view in an unbiased way, not having to worry about labeling anything except for spritzing in the dye, and then taking time-lapse movies where you don't have to worry about bleaching, which is nice, and also don't have to worry about phototoxicity, which is a huge problem typically for especially super resolution microscopy, where you have a very limited photon budget before your cells go belly up because of the toxicity that the fluorescence process generates. Yeah? Here, in this case, the dye molecules on the outside doesn't accumulate inside the cells and can be washed away, and they'll be expected to be much less harmful. Right? So we can take these time-lapse movies here. Striking is still my all-time favorite, where you can see a cell, a putative microglia cell, immune cell of the brain, traversing across this cell body here, and you get a sense for the mechanical nature of the motion, right? It's not like there's some enzymatic degradation of the extracellular space, extracellular matrix going on. It's just the cell just plowing through it, right? This is minutes, so, but it's not diffusing either. I mean, it seems to have a mind of its own, right? It's doing something. It has a plan. It knows what it's doing, right? Another example is shown here where we provoke this kind of activity, this kind of migratory behavior by placing a laser lesion here, damaging the tissue on purpose here in the center. And we see the arrival of the cell. And this is in minutes here. There's some other friends, reinforcement coming, checking it out. And I'm going to reloop it. And what's, I think, remarkable here is to see, the neurons are sort of staying put. They're not moving at all. They're like, caught in the fire, right? But the cells, these microglia cells, they can go anywhere, and they can respect some sort of code of the street. And they're not going straight to following some gradient, some radial gradient. But it's respectful here of this lineup of cell bodies to reach the final target. Right? The next step now we're pushing this to do this not in brain slices, but brain slices maybe just a curiosity to do it there. I think it really be really fantastic to do it in vivo, where you have the right amount of cranial pressure also, and you have vasculature, functioning blood vessel system, and so on. All of that is obviously you don't have in brain slices. Just to show you, just a sort of proof of principle. The image is still not still looks very terrible, but the effect here, I just want to see one thing here. These stripes here, this striation is not the microscope moving. It's actually axons running across. So we have the resolution to see axons, which are something like 200 nanometer wide, and we can see them in vivo in this inverse labeling sushi strategy, and that tells me we are on a good track. Yeah. Okay, so I've hopefully you enjoyed this part on super resolution shadow imaging. Not just a technique to image the extracellular space, which is our parting mission, to develop a technique in a live brain tissue context to visualize extracellular space, but turns out with a bit of imagination, with reconstructions and so on, actually you can use it just as a brain imaging technique, like regular two-photon microscopy. It's just that you don't see one cell, you see all cells, which is obviously daunting because maybe you're seeing too many things, and you're getting distracted, and you actually may not also sometimes always have the necessary resolution to really see the fine details. But a priori, there's no physical limit to the kind of resolution we can achieve, because we can now just increase it. We can increase the laser power. Why not? Get more resolution, yeah? Sets resolution scales with laser power, but we don't have to worry about frying the cells, because we are not touching the cells, right? We are touching the stuff outside, so the cells are much more happy. Also, we can increase the dye concentration a lot by factor 10 outside or something, because the cells also don't seem to mind. Yeah? Whereas intracellularly, it's hard. If you go too high, the cells won't like it. Yeah? So a priori, I think we can get nicer images, sharper, and we should at some point, just with engineering, with more adaptive optics, better design of the microscope, achieve a resolution of maybe 20 nanometers isotropically, X, Y, and Z. And I think if we have 20 nanometers, that's all the resolution we need for really definitive morphological anatomical reconstructions, yeah? in a kind of dense way like the EM community is doing. So then exactly, so this is then the midterm goal. And then the perspective now is to also, actually we're doing this right now, combine it with positive imaging using GCamp, expressing it inside the cells. Again, inside is black, so there's no issue of having an elevated background or something, so we can combine it with regular calcium imaging. And then also to combine these two super resolution techniques to probe the extracellular space. Sushi gives us access to the anatomy, the topology, if you will, and this super resolution tracking actually gives us access to the diffusivity. It maps out in another high content way the morphology as well, but it's not really good at that. It's better at actually looking at diffusion, and probing the micro domains and the nano domain of the extracellular space, right? And then applying it to other organs and going in vivo. Okay, now I'm very late. I have 10 more minutes? 7 minutes? Okay. So I want to present you another more methodological thing, combining super resolution techniques, STED and single molecule based imaging. And this is also just, it was published and went online yesterday. So very happy, yeah, you can look it up there. All the details are online now. And also if you understand this picture here, you also have learned the lesson for today, second lesson for today. So the idea here is, so this was, we tried to get the cover, we didn't get it, but I can present it here in this talk, which is, sort of a STED ring here, right, around it, like a bull's eye or something, and then inside of it we can see clearly, and we can see the molecular tracks of the receptors, synaptic receptors, because that's what we're labeling, that's what we're interested in. And we can see the tracks and nicely how they move around the little molecules in the various morphological compartments, the spine head, the spine neck, and the dendrite. So this was the goal of the microscope, basically, of that platform, to have a system that gives us a nice anatomical readout. Really see the nanoscale anatomy of the spines, and for that, a deterministic, like STED, super resolution approach is really ideal for that. But then combine that with the ability to localize and to measure the position and movements also of single synaptic proteins. Okay, so synapses are micron-sized, submicron-sized devices. Very complex molecular organization, pre- and post-synaptically, and there's lots of things that are on the order of double-digit nanoscale dimensions, yeah? And some of them have these orderly structures, like membrane-enclosed things, like the terminal, the presynaptic terminal, or the postsynaptic spine, or vesicles, right? Very sort of regular, recurring structures, and then you have the protein complexes inside the PSD and so on, the active zone, which have their own irregular dimensions, right? And it would be nice to be able to visualize both aspects, these more regular structures and membrane-enclosed cell morphology versus, and also the molecular players of the synapse, right? Okay, so then we built a microscope. And it's basically just two microscopes built into one. So there's synergy in the sense of that we get synergy, biological synergy, but there's no technical synergy actually. The two are really separate. Now there's the left wing, it's the STED microscope, and on the right side we have the single molecule imaging. The STED imaging, as you know, as before, point scanning technique. In this case we use a one photon excitation process, STED depletion as before, and then we use this 3D optics based on adaptive optics, spatial light modulators to create the 3D donut. Yeah? And this is routed into the microscope. And then on the other hand, we have wide field imaging in TIRF mode, total internal reflection mode, to image very close to the cover slip. Now this is all in plated cells. Image and localize single molecules, single molecule, single emitters, right? And there the techniques are called, PALM, STORM, U-Paint, what have you, right? So here the challenges are, and I don't have time to go into this, first is the spectral separation, that you don't want any crosstalk between the left wing and the right wing. And we worked out a solution, a spectral combination that is okay, just using standard fluorophores and dyes. Yeah? So there was no new development necessary. Then the technical issue was really to align the two imaging modalities at the level of single digit or double digit nanometer resolution. Yeah? And that's where it gets a bit hairy, because there's all kinds of non-linearities actually in the images. Yeah? CCD camera image is not a linear thing, really. Yeah? And certainly not a scanned image is not linear. And on the edges, you have a lot of distortions, and you have to account for them. And so you need to retransform them. And then, but you can do that with fiduciary markers. You can then really create a grid that is reliable to within or to below, tens of nanometers, 10 nanometers here. And then we need to be able to rapidly switch between the two modes because we want to correlate one, the morphology with the molecules. And the thing, both being dynamic, there's an issue if it takes too long to switch back and forth between them. You lose the correlation, right? So you need to, within seconds, be able to switch from one mode to the other without having to realign the system. And it should be automated, and you just press a button on your software to do it, right? So that took also a while to just technically to do. Yeah? This was an engineering challenge, yeah? But we solved it. Yeah? Trust me. Yeah? So then just show you now a few images. So here you see stat image of this, the dendritic morphology, spines. Then we image the scaffold protein, PSD95, in the postsynaptic density. Using PALM, UPaint gives us access to the diffusion of glutamate receptors on the surface of the cells. So it's a surface-based labeling strategy. And then we can overlay it. And then you see here, in this example here, the location of the PSD95, and then the location of, in the wiggly tracks are the locations, the tracks of the GluA1 receptor, the surface receptor. It's not inside the cell, but on the outside. And you can see here the color here codes here also for the speed. And you can see here there's a spinule, a little thing, very small little thing coming out of the spine, like a mini spine. And they are very hard to see with regular confocal microscopy, but we now see jutting out from the spine head, and then we see actually the receptors, even though the structure is so small, are super fast moving. Yeah?
Are you using the dynamics in the STEP for this particular? You said you need to switch between them quickly because you want to capture the.
Yeah. So we take a.
But in this particular example, you don't really need the movement in the STEP image, right? It seems to be static here.
Yeah. Well, the spinule is dynamic. It moves within 20 seconds will have moved. Yeah, and then
correct for that image. Did you correct for that movement?
You cannot really because it's not it's not just a translation or rotation. It's just this thing moves. Everything else maybe stays the same. So it's so you have to just do it basically more or less at the same time. We can't do it really concurrently. We could. It could be done concurrently, but it's within a few seconds. Yeah.
So what are
The traces are the tracks of single molecules. And they are, right, so this is a sparse, it's not a sparse labeling, it's a sparse activation. I didn't go into the details. The way UPaint works, or PALM for that matter, is that you, at any point in time, you have a low number of single emitters in your image that are physically separated by more than the diffraction zone. Because if they're within the diffraction zone, you cannot resolve them. But so you activate, you use an activation laser for a case of PALM, 4 or 5 UV laser, that activates just a very low fraction of these molecules. They are photoactivatable molecules, fluorescent proteins. So a low number of them, and then you register them, you track them, right? And then you do that actually thousands of times. Yeah, and then reconstruct a large, very dense image. Yeah. And then, and now close out here, we can now correlate the morphology in detail with the whereabouts and the dynamics of the single molecules, in this case synaptic receptors and scaffold proteins. And there, I just want to highlight here out of the fact that I just already mentioned, that in the spinule here, the structure, the little mini spine, we have, when we look at the diffusion now of GluA1, which is a subunit of the AMPA receptor, the main glutamatergic receptor channel in excitatory synapses, we look at the diffusivity, so the mobility of this receptor at synapses or in various compartments. We see that in the PSD, it is very slow. This is a log plot now of the diffusivity, right? So -3, so it's a really small number, right? And this is basically where the receptor is immobilized. So once it's in the PSD, it's trapped. It doesn't move around a lot. Whereas when it is on the spindule here, this is the outermost distribution here, it just whizzes around rapidly. Yeah? And this is by almost 3 or 2.5 orders. Yeah? So it's 100 times faster moving. And it's a bit curious that it's moving so rapidly in this spindule where you would think maybe the motion is constrained because it's sort of like a one-dimensional structure only. It's only a little, I don't want to say penis, but it's, it's a little finger that comes out, but yet it moves very rapidly.
Are those gluer molecules there are actually the stools, or is it like the ones that are already used in SNAP and then going backwards, like in sort of a degradation or something? Like, why are there gluer receptors in the spindle? What are they doing? Are they also functional there?
We haven't now looked at their physiological action, but presumably they're on the surface. They're in the transmembrane, and they should be functional.
So are they on the membrane or inside?
They're on the surface, yeah. Because the way we label, I didn't go into the details of that. The labeling pre-selects out for that. For only surface receptors are labeled with this U-paint technique. And then we can combine this with time-lapse imaging, so that we can cycle back between STED imaging and single molecule imaging. And it's just to show that technically it's possible, and you can imagine now kinds of experiments we could do. We could do some LTP type experiments, look at how receptors change vis-a-vis a changing morphology. Because we know, and this is something that Florian started some 20 years ago, that LTP and all these synaptic, there's a lot of synaptic remodeling and morphogenesis going on with altered levels of neuronal activity. And it would be interesting to see how that pairs while also receptors are changing and receptors are being pushed into the synapse, right? So it's definitely be interesting to see both at the same time. And then we also use the sushi technique in the plated cells. Here, this is a growth cone. It looks like a sick-looking neuron, but it's actually very physiological. So don't worry. So this is the end of a developing axon, growth cone, and we can now inversely also label it, and then combine this, so the sushi in plated cells with a single molecule imaging. The big advantage here is that these young neurons are extremely sensitive to light dosage. If you go in with a STED light, in a positively labeled growth cone, you will kill it. You will to smithereens. Right? You will be fried before you know it. And this is not the case in the inverse labeling. Also, it's hard to label growth cones robustly because they are young neurons and they don't express GFP very nicely. Right? So this is a nice workaround. Okay, let me just conclude and take you to the last acknowledgement slides. So the sushi was done in the lab by Jan Tönnissen, former postdoc who has his own group in Bilbao now, together with Krishna Inavali, who built a 3D module. And he's now also trying to get a permanent position. Didn't talk about Misa's work. And then Stefan is doing the in vivo aspect, pushing the sushi in vivo. And this, the single molecule imaging was done in collaboration with Jean-Baptiste Sibarita, who's an expert in storm and palm imaging. And we're looking for people to join us in Bordeaux. Thank you very much for listening. Mm-hmm. 50 microns. Now we're extending that. So we hope to get maybe 100 microns in with adaptive optics. And whether it's a slice or in vivo should make no difference. In vivo you have obviously more motions to worry about. You have to image more rapidly or do some sort of active image stabilization, which in the brain slice is not necessary because it's really, you can keep it steady easily.
What kind of exercise
Yeah, there's a lot of directions we can take now. We can turn this. In my mind, exercise space is really uncharted. It's a really a terra incognita, and there's lots of interesting things. One particular issue, for instance, is just want to see what happens during a day. What happens with the extracellular space? There's been some reports that during sleep there's a change in the extracellular volume, and that there's sort of a broadening of the extracellular space, and this could be one of the functions of sleep, to broaden the extracellular space, and hence create a different dynamics for clearance of metabolites that accumulate during the day. But there was a lot of indirect evidence for this, and we could now just let the mouse fall asleep under the microscope and see what happens. Are there really consistent major changes in the extracellular space or not, and how does that then tie with flow processes, material transport processes from the vasculature, from the perivascular spaces into the neuropil.
So astrocytes and microglia cells together, they form outline of neurons. And this is now reflected in the Swiss imaging. And is it that it only picks up a small percentage of these glia cells?
Yeah, so I would disagree actually with your statement that they far outnumber. That was the thinking a while back, but now people have sort of corrected the numbers. It used to be people say, oh, they have 10 times more glia cells than neurons. Is that what you think?
Yeah.
But it's not. That's not true. It's now people say it's really 1-to-1. And there's been recent studies that quantify. And it depends certainly on brain area and so on, but overall, it's not. That wasn't confirmed.
So you're seeing all of the cells not missing significant part of the cells available, right? Is that right?
Yeah, so we haven't done really quantification, but for my just feeling is actually, I would say in the hippocampus, neurons outnumber glia cells. But then people have done more detailed analysis, and I think it comes down to like roughly 1-to-1 overall.
Yeah, I'm just curious. Have you ever captured the exosome secretion in your imaging?
No, but that would be interesting. Yes. And we can see the inverse. Endocytosis. We can after a while, the neurons are really do a lot of endocytosis constitutively. To actually we see really puncta inside the neurons, and they are brightly labeled, and then move inside in the intracellular space. And people have I think used that in the past also. But I think now they haven't used it really with 3D STET and so on. And we could track that. Yeah. But the exosomes would be interesting too.
All right. Thank you again, Paladin.
So, sorry, it was over time.